So our next presentation is going to be by Rahul Ghosh and by Jack McEachran. Rahul is a recent PhD student from the University of Minnesota and in computer science, and he's now at Google. And then Zach is with the North Central River Forecasting System with NOAA.
Thanks, John. All right. Excuse me. Okay, thank you for the invitation to speak. I'll be presenting on research and a collaboration between the NOAA National Weather Service and the University of Minnesota. So thank you to my colleagues and collaborators throughout NOAA and the university. So I'll be going to talk about a new approach to model multi-scale, hierarchically interacting processes using knowledge-guided machine learning. I think this actually is a very good follow-up to the previous couple talks that we have had. The specific application of the model that I'll be focusing on is modeling streamflow and flood forecasting in an operational setting. However, the methods are broadly relevant. So let's think about physical hydrology. In this perspective, streamflow is the vital sign of a catchment. So you and I go to the doctor and get our blood pressure and heart rate taken. And these things we don't say are the equivalent to our health, right? They're just sort of indicators or metrics that we use to get an idea of the sort of emergent property of our health that's underlying these. It's kind of similar in catchment science. We take our stethoscope and we put it up to streamflow and we try to figure out what's going on in the landscape as a whole. So in this perspective, you have some input, precipitation come in, something happens, and we get an output of streamflow. So that something happens is what I'm really interested in. Critical to those processes, to that something happens, is underlying catchment states relevant for runoff generation, such as soil moisture, runoff, groundwater, etc. So in terms of a physics-based model, we have, again, weather coming in, and we use our understanding of the physics to estimate catchment, the underlying catchment states. As the hydrologic cycle evolves, states interact and evolve at different temporal scales. This is critical to the theory, right? Some states change quickly over the course of hours, like when a large storm overwhelms our surface soil moisture storage and the soil can't accept any more water. But some change slowly, like monthly or even greater timescales, like mountain snowpack or Minnesota snowpack. States also interact. So, for example, quickly evolving soil moisture near the surface of the landscape, so responding to that storm event, partitions into plant water use, such as evapotranspiration, which itself can change at hourly, daily, and seasonal scales, and downward percolation into and recharge of slowly evolving deeper soil zones like groundwater through time. This soil moisture storage near the surface also contributes to how much incoming rain or snowmelt will become flood-inducing runoff. So how does the National Weather Service fit into water? I'm currently working at one of the 13 river forecast centers in the United States, the North Central River Forecast Center in Chanhassen, Minnesota. The River Forecast Center network provides official river level forecasts for 3,600 river gauges throughout the United States. Complementing the RFC forecast is the National Water Model, which provides grid-based forecast guidance. However, this presentation will benchmark against the official NOAA river forecasts generated by river forecast centers. So let's get into some of the deep learning discussion. Currently, the sort of leading machine learning-based streamflow model is the LSTM model, which is often cited as kind of the model to beat for prediction for streamflow, and often performs better than physics-based models right out of the box. Conceptually, this is a forward model where you take in your inputs, you run your model, and you get your output streamflow as a result. However, forecasting is not the same as modeling. Yes, you need good models to do good forecasting, but there are unique considerations when it comes to forecasting, many of which have to do with the fact that we're dealing intrinsically with time series. Central to forecasting is the idea of data assimilation. Streamflow is just the output of most models that we use, but at every time step, we gain a new observation as long as the gauge is working. Observations can drift away from the simulations for many reasons. To assimilate data, we often nudge the internal states of the model to bring the simulation in alignment with the observed. Here's an illustration of the point. Here's a catchment in yellow state lambda. We can see the target time series we're forecasting here, stream flow through time. The vertical yellow line represents T naught, so the observations that will eventually occur, the black line, are unknown to us to the right of the yellow line. The simulation of our catchment model is shown on the yellow dotted line. Now let's advance our T naught. Now in between the yellow and red lines, the black line is the observed stream flow, and the yellow is what our simulation had for that time period. Obviously, something is wrong. So we nudge our internal catchment state, either manually or through an automatic method, such as ensemble-Kalman filtering. The new state is alpha. This lines up the forecast with the observed between the yellow and red initialization lines. And if we look into the future, we can see that our forecast was much better after having adjusted our catchment states. At river forecast centers, a manual process is used where an expert forecaster synthesizes many different sources of information, such as satellite imagery, field reports, and historical analogs to make best judgment modifiers of catchment states. This is a manual data assimilation process that uses a sort of human in the loop paradigm. I'll give you an example here from a forecaster shift log. So here's a forecaster writing during a spring snowmelt flooding event. Generally speaking, the eastern basins are showing more melt than the western basins based on the response. This goes for the entire region. So I did a lot of letting the melt ride or positive melt factor corrections on the eastern basins and some slowing of the melt on the western basins. I used the Sentinel-2 pass from April 12th as a way to determine where snowpack was ripe and melting. In another region, these took off in the middle of the night. Similar to what my colleagues did in the northwest corner of another forecast group, I added water to the lower soil zone bucket up to 2 inches and bumped up the melt. This made the simulations line up very well. However, this human in the loop process is very expertise intensive. It takes a long time to train, and it can be prone to human error, even though these forecasters are experts, if I do say so myself. But automatic data assimilation routines can be very computationally expensive, especially if you need to run the assimilation over the entire country and get an answer within the matter of moments. As well as both with the manual and the automatic routines, there's still a lot of uncertainty in how to change the states, which states are best to change. And you might change your states and then be really good for this current flooding event, but it gets your states out of whack for the next event. So if you change sort of overfit, you might sacrifice long-term performance. But putting a human in the loop, so using that manual process, increases trust in the ability to communicate the modeling to partners, including shortcoming. So yes, I added water to the lower soil zone, but this is what's happened in the past when I've done that. And here's some historical events that this event seems to be similar to. And that means that I maybe think that the peak flow will be between this and this based on my observations, right? And in this business, that sort of communication with partners who are doing the hard work of putting up sandbags, for example, is really critical. And excuse me, I lost my place. It's a very critical element of the whole enterprise. So oh boy. As I discussed earlier, the LSTM approach is one of the most popular and highly skilled. However, to develop some kind of data assimilation capability, we can use an autoregressive LSTM or LSTM-AR. And so effectively, we just add in the most recent observed stream flow as another input stream into an LSTM. And it's really good. It has a very high model skill, and it's very efficient. However, let's kind of move on to building up the model that we've developed. So both LSTM and LSTM-AR are deep learning sort of black box approaches that do not account for hydrologic science. They're trained on historical data and possibly basin static characteristics, and then take the system inputs to generate the outputs. So they're both forward models. I want to highlight the distinction here between forward model and inverse models as we look to build an even more robust method that incorporates insights from hydrologic science for hopefully an even more skillful, but also interpretable approach. An inverse model takes the system response or output, as well as the inputs, and estimates the system's underlying characteristics. Imagine a model that takes in precipitation and the observed runoff and estimates, for example, how much sand is in the soil of the catchment. However, inverse modeling can also estimate time varying system characteristics or attributes or states. So at this point, I hope some light bulbs are going off as we build this up. So can we use inverse modeling to mirror the operational hydrology process, where currently I'm in the loop changing states if I need to bring simulation in alignment with observations? Can we use inverse modeling to sort of do that step? And can we specify that, well, there are these states, some very fast, some very slowly, some very kind of in between. And by the way, let's allow these states to interact with each other. Once these catchment states are reconstructed based on the inverse model, we can then feed it into a forward model to generate a forecast. So here's the overall diagram for our modeling approach, which we've termed the factorized hierarchical neural network, or FHNN. Now we're going to look to see how the FHNN performs compared to NWS physics-based model, the Sacramento Soil Moisture Accounting Model, or SAXMA, and the LSTM and the LSTM AR. So note that our FHNN approach is going to take in the same inputs as the LSTM AR: precipitation, temperature, and the most recent observed stream flow. It's run at a 6-hourly time step, and it's at the catchment scale. I'll be reporting model performance using the Nash-Sutcliffe model efficiency, known outside of hydrology as the coefficient of determination. So 1 is the best and 0 is really bad. So here are some results for the coefficient for the Nash-Sutcliffe efficiency for 7-day forecasts. The wide bottom table are for all 14 catchments for which we're doing the test. The summary statistics of the model performance NSE values are at the top table. You can see that the LSTM has more skill. The FHNN has more skill than the LSTM and the LSTM AR in all categories, in addition to more skill than the NWS physics-based model used at the River Forecast Center, the SAXMA model. Given the same input information, the FHNN and the LSTM AR, the only difference is the sort of model architecture. The minimum model performance of the FHNN has about the same level of skill as the median SAXMA performance. You can also see substantial skill improvement, particularly for poorly performing catchments. The minimum is much better for FHNN compared to the competitors. On the high end, FHNN shows the best performance of all options. We know that machine learning models live on data and are improved with more and more. So if we build a global model where we're able to look at all of the catchments at once, we can compare this, the model performance of the basin by basin ML models. So we can see here that when a global model is trained, the minimum performance for the FHNN improves significantly. The FHNN outperforms all other state-of-the-art machine learning approaches within streamflow prediction for the performance categories and quantiles. And the performance advantage of the FHNN still obtains compared to the physics-based model. Another benefit of machine learning models, particularly those influenced by physical process knowledge, is they can learn the basic physics from a physics-based model during training. So if we use the SAXMA model that NWS uses, which does incorporate important physics, it's incomplete. But we can generate decades of hydrographs from the SAXMA model. So we can train on that SAXMA model, which is that right-hand column, and the left-hand columns does not train on SAXMA. So we can see on the leftmost columns then, we can see how many true observations we're using in the training period. So we train on 50 years of SAXMA plus just a little bit of observed data. And we can see that the inclusion of SAXMA in the training period, adjusted by observation, considerably increases model skill. Let's look at the case where we have the SAXMA model and only half a year of observations to train on. The median NSE here is 0.75, compared to 0.3, where only that half year of observations was used to train the FHNN with no SAXMA. Additionally, the 75th percentile model performance for SAXMA itself has an NSE of 0.73. So using SAXMA plus only a half year of observations is already better performing than 3/4 of all SAXMA models we tested. So now we've compared the FHNN to other models in question, right? But here's a nice, any next generation fans out there. It's from the episode called Measure of a Man. And the Captain Picard has to argue, like, what makes somebody human? Oh no, 2 minutes left. And so what makes, Data, the android, is he a human? Is he a person or not? So the Weather Service uses a human in the loop system, right? We're not just using that basic physics-based model, but we're using our expertise to modify this. So what's sort of the measure of an operational hydrologist? So to do this, we gave the same imperfectly known future precipitation forecast to the FHNN and compared it to official National Weather Service forecasts, where we were using both the physics-based model and our expertise to adjust the forecast. And the result here, you can see the lead time on the x-axis and the difference in model skill on the y. You can see above 0, the human is more skillful than the machine learning model, but below that, the FHNN is more skillful. And we can see that once you account for these uncertainty bounds, within the first 18 hours, the human forecaster is still more skillful than the machine learning model, even though the machine learning model is much more skillful than the baseline physics-based model that the machine learning model beats at all timescales, right? But the FHNN is more skillful than the human forecaster in the kind of medium days 2 to 4 of that forecasting window. So FHNN is more skillful than the baseline physics-based model and the other state-of-the-art machine learning streamflow forecasting models. But during an actual flooding event, a human forecaster using a physics-based model is still more skillful than the machine learning model. However, is the FHNN model interpretable, and could a human adjust or interpret the machine learning model to get the same skill increase that the forecaster can gain on top of the physics-based model? Could you have a human in the loop for a streamflow forecasting model? And this is my final point here, I promise. So to test this, we trained the FHNN model on precipitation, temperature, and the historical simulated streamflow from SAXMA. So here we didn't show it any of the underlying states or anything like this. But inside of the FHNN, we can see that, so here's the soil moisture in the summer of 2013 in a basin in Iowa, the state value on the Y, just arbitrary, and the time on the X. You can see that the internals of the FHNN is uniquely suited to and does build an internal representation of the states that may be interpretable by a forecaster. So we're hoping that across, if we're able to better integrate human expertise on top of the kind of knowledge guided expertise within the FHNN, we can improve forecast skill at those long lead times based on the automatic sort of architecture of the model, but in the short lead times based on the expertise being able to interpret the model and hopefully improve upon the model using those manual data assimilation processes that the Weather Service already has in place. And I'm happy to take questions whenever there's time. Thank you.
Nice job there. We have time for questions. So, who is this?
Thanks, Zach. This is a social science question, so I'm sorry, but I'm interested in the perception kind of within the forecasting center of letting a machine do the tweaking instead of the human. And I mean, I think you answered the question, which is like maybe a human can oversee the machine predicting the states and making the adjustments, but I'm just interested in kind of the perception from the forecasters themselves.
Yeah, I think there's some really awesome opportunities for social science research in that area, which I don't know is kind of an easy answer to give, right? More research is needed. But I do think that we've been kind of building this research like from the inside out. So it's, I think, the sort of the hope for this and the sort of acceptance of this has been much better than if it's been sort of like imposed from on high within the organization. I think we've also, the services the River Forecast Center has offered within the recent, the most recent decade, let's say, is way more than when the River Forecast Center was founded or last modernized in the sort of 90s, early 2000s. So we used to do like maybe daily time step 3 days ahead. And there are stories of like we used to call the USGS gauge to like get the data, and there were way fewer points that we were responsible for forecast for. So the current very labor intensive process that we use is kind of based on a paradigm where we had to do less. So now I think that like staffing and expertise is really can be stretched thin at times. And so I think there's a recognition that like our processes need to evolve, but how exactly that works is unclear. But the recognition is there. So there's been a lot of, I think, excitement about something like this because it's really easy to kind of have this dichotomy between either it's a really human intensive physics-based process or machine learning is going to come and take all of our jobs. We've kind of been able to thread the needle in the communication between like, hopefully we get a little bit of the best of both worlds here. But I think the sort of broader sense of perception as well as where the agency is going, like those discussions are above my pay grade, right? But I think there are discussions at very high levels ongoing right now about what's the future of the NWS forecaster look like. And I think there's a certain, faction that hopes that we can eliminate the human from the sort of like hydrology part of the forecast. And I think what our work is showing is like, if we do that, there might be a service degradation. Like, even though we can show the machine learning models can blow the physics-based models out of the water every time on paper, when you actually compare to the forecasts that are issued to the public where we've been able to add our value, like it's not a given that just model skill is just going to improve to the moon. And so what the agency does with the information, I'm not sure yet. Yeah, good question.
So,
Very quick question, please.
so you presented results for all the basins together. Are there basins for which the machine learning model works better than humans, and there are other ones for which humans work consistently better than the?
Yeah, the exact point where the humans being, using the physics-based model being more skillful than the machine learning-based model, like whether it's 18 hours, 12 hours, or like 2 days, that like intersection point changes based on the basin, but it's pretty common based on all of our basins that like within that very short time period, the human forecaster using the physics-based model is more skillful. But again, the exact like how that shakes out with the lead time is different based on the basin. And I think some of that depends on the type of flooding event. Is it a very fast responding urban basin? Is it a very slow snowmelt type flood? So there's definitely, we can parse it more than we have. Yeah, I think that's a great suggestion.
Okay, I think we should move on. Thank you, Zach.
Yeah, thank you.